Our next topic is interface engineering between high-K material and semiconductor substrate. So interface engineering plays major role to get for the electrical performance of the device. If the interface is clear and stable, then the voltage at the VI characteristics and CV characteristics are really reasonable. So if the interface is not stable and it has some disturbance at some places, so by that time the IV characteristics and CV characteristics may get disturbed and we won't get any particular shape in the plots. So that we should know clearly about the interface engineering in the fabrication of MOS devices, metal oxide semiconductor devices, whether it is MOSFET or MOS capacitor. So in interface engineering, whenever you deposit high-K material, as we discussed about the appropriate high-K material is hafnium oxide for the current industry. In the current industry, people are using all microelectronics industry people are using hafnium oxide for the microelectronic devices. So whenever this hafnium oxide generally deposited by using different techniques, physical vapor deposition techniques and chemical vapor deposition techniques, such as sputtering, molecular MOCVD, ALD. All these techniques people are using industrially, people are following to deposit thin high-K layer. Here I quoted thin. Thin means, so initially people are using native oxide, that is silicon oxide and metal stacks for MOS devices. But this silicon oxide is a low-K material, dielectric constant is only 3.2. Low-K material, if you keep on reducing the size, because we are always looking for very thin devices and small devices. The thin and small devices are performing are acting like smart devices. So whenever we call everything as smartphone, smart TV, smart everything is smart right nowadays, electronic devices. So that for getting smart devices, thin devices, we have to concentrate on miniaturization. With miniaturization only it is possible to have thin devices, very small devices. So if you keep on reducing, see, silicon oxide is at micron level it is okay, at micrometer level it is okay, it is performing, it is effectively stop the ejection of electrons or flowing of electrons from metal to semiconductor or semiconductor to metal. That means it effectively stops the leakage currents. So forget about the storage capacity and all, okay, it effectively stops the leakage currents at the micrometer level size. Whereas if you keep on reducing the thickness of the oxide layer on semiconductor up to at the nanometer level, by that time silicon dioxide is not performing well and those devices are showing high leakage currents. Whenever the device showing high leakage currents, then it is not that particular material is not suitable for the device application. So that people started thinking on different high-K materials as we discussed in the earlier class, and finally they choose hafnium oxide. Hafnium oxide as dielectric constant 25. This titanium oxide, tantalum oxide, zirconium oxide, hafnium oxide, all dielectric materials have dielectric constant of 25. Among them, this due to conduction band offset values, valence band offset values, thermal and chemical stability with the semiconductor substrate, by considering all these parameters, people choosing hafnium oxide. If the hafnium oxide size reduce it to more than less than 10 nanometers, less than 2 nanometers, less than 1 nanometer also, it is performing well for the by showing low leakage currents. So that hafnium oxide is useful for the miniaturized devices. So in the interface engineering, people mainly concentrate on interface state density values. Those are main defects. These interface state density generally occurs in this way. I will tell you a small story. So silicon valency is 4. So this silicon has 4 valency bands with the surrounding atoms. So whenever the foreign atom, because we are cleaning the silicon substrate and we are trying to deposit foreign layer on the silicon substrate. So this foreign atom is coming and accommodate on the silicon surface. Due to this collision or external force applied on the silicon structure, atomic structure, the top layer atoms get disturbed, and this covalent bond, the top layer electron will go off. By the time the silicon covalent bond on the top layer, the top surface occupied silicon atoms is suffering with less lacking of electron in the covalent bond. It has only 1 electron at silicon side. At the top side, at the bottom side, it has one electron. At the bottom side, the electron has been removed due to the external force applied, so that this electron has been removed or dislocated outside. By the time this covalent bond is vacant with 1 electron, vacant, it has only 1 electron. It is trying to absorb the other electron by vibrating like this. So that particular bond is called dangling bond. This dangling bond is the main resource for the interface state densities. So those are how to reduce those dangling bonds. So it is not so okay. We clean silicon and we deposited a hafnium oxide layer on the silicon, and finally we have our stack, that is silicon hafnium oxide stack. But later we just paste the aluminum paste or something silver by we just apply on the surface, and we can measure the CV curves. By the time we can get CV curve, but the CV curve maybe the CV curve generally capacitance voltage curve has accumulation region, depletion region, and inversion region. This accumulation region may be stable because of good interface, thermally stable interface between hafnium oxide at the metal and semiconductor. Because hafnium oxide we deposit, that hafnium oxide is stable, it cannot go easily like germanium oxide, so that we have good accumulation region. Whenever coming to depletion region, depletion is a direct definition of the interface of the oxide and semiconductor. If the interface is severely struggling with so many defects like interface trap densities, by the time this depletion may get stretched, or some bumps and kinks may appear on the depletion region. These bumps and stretch or bumps and kinks may be reduced. The people have been started thinking how to reduce them. So then they started the process of annealing. So after depletion we will get inversion region. That is a separate story, we will see later. So these kinks and bumps are stretched, how to reduce, and people started annealing. So when you perform oxygen annealing, maybe by the time oxygen annealing and parallelly hydrogen annealing also. So see, this oxygen annealing may give more stable interface, because whenever you perform oxygen annealing in silicon's hafnium oxide stack, this oxygen is diffused to the silicon surface and may accommodate, because silicon easily form silicon oxide. So they may form silicon oxide underneath of the hafnium oxide. So this is again one disadvantage, because silicon oxide is low K material, hafnium oxide high K material. The series capacitance may reduce the final accumulation capacitance value. It is not good for the memory applications. But whenever you perform hydrogen annealing, this hydrogen annealing cannot form any silicates, right? Silicates. So silicate, but that silicate is not a dielectric material, even forming also. But this hydrogen went through hafnium oxide and have the some and participate in the covalent bond, because hydrogen has one single electron. That single electron is accommodated fulfill the valency electron for the silicon covalent bond, and the hydrogen will try to reduce the number of dangling bonds underneath of the hafnium oxide above the silicon surface. That means interface of the hafnium oxide silicon. Finally, it is effectively reduce the interface tab densities in between underneath of the hafnium oxide at the interface of silicon hafnium oxide. So here we can see some interfaces in the HREM images also. These are germanium. One is this work I only performed this. Done this work during my postdoctoral, and one is germanium substrate and the silicon substrate. So we can see the germanium substrate interface, germanium hafnium oxide interface, and the silicon hafnium oxide interface also. So to measure the DAT level, we have some simulations. MathCAD, by using MathCAD, we can extract DAT values as well as EOT values as well as effective work function also. So for reference, some references also I had given. So this is information about the interface engineering. That interface engineering plays very crucial roles in the device properties, final properties, electrical properties. Okay.